Hey guys, so I'm going to do a video. This is the number 14 from our in-class review today. A lot of people were missing today, and I also think for the people who were here, a lot of people would like to see this problem done again. So I'm just going to go through and make a video of it. I hope you find that helpful. This is, I know it says here, adapted from the 2018 AB Calc exam. I think this might be just the exact problem. I can't remember if we made any changes to this one. But if you want some additional resources, if you Google the 2018 AP AB free response questions, you can find this as well. So let's go through this. It says the graph of the continuous function g, the derivative of the function f, is shown to the right. I'm actually going to pause here because they just gave me some really important information. They said we have the graph of the continuous function g, but here's the important part. It's the derivative of the function f. So g is the derivative of f. That's important. Okay. The function g is piecewise linear from -5 until 3. So you'll notice all of these pieces are linear. And then starting at 3, I now have a quadratic, and it's defined for me here. So this curve here has been defined as 2 times the quantity x minus 4 all squared. So let's just jump into the first part. So part A says if f of 1 equals 3, what is the value of f of -5? So I need a function value, and you'll notice I don't have any information about f. I only have information about f prime. So I need to use f prime somehow to get information about f. Well, we know from this unit that if I want information about f, I'm going to need the antiderivative of f prime. So there's my starting point. So I'm going to take the antiderivative. But remember, when I deal with this, like when I plug in values, it's not like a derivative where if I want f of 1, I just plug in 1 to get an answer. I'm now going to do a range from 2 different values. I need to take the antiderivative. I'm going to find the change from one value to another. So let's think about the information I have. I want information about f of -5. I'm going to leave some space here. Okay, I want information about -5. So I'm going from somewhere to -5. Well, what do I already have information about? I have information about f of 1, or what's happening at the function at 1. So I need the change till -5. Now, on the test and on the AP exam, you can't use a highlighter, but I just want to point this out real fast. This value here, where I started, should be the start for my antiderivative, and then I'm going until -5. Okay, so let's see if we can evaluate this now. We know what f of 1 is. It has a value of 3. Now this is flipped. I'm really going to do the area under the curve because remember, g is f prime. This is an f prime graph here. So I can do the area under f prime to get information about f. Okay, well these are flipped. So the first thing I'm going to do is rewrite this as minus from -5 to 1. Start moving this way because I'm running out a little bit of space down here. So equals 3 minus, well let's see if we can find the area under the curve. I want it from -5 until 1. So I need all of this and this. Well, from -5 until -2, I have a rectangle, but it's below the x-axis. So if I want to find the area of this, it's minus, because it's below, width times height. Now I have a triangle. It's below, so 1/2, width times height. I have another triangle, but it's above, so plus 1/2, width times height. Now remember, this is a numerical answer and it's free response, so I can actually leave my answer just like this. I honestly wouldn't even take time to go through this to simplify, so just leave it like that, because if you simplify and make a mistake, you'll lose points. So now let's go on to part B. Part B says evaluate the antiderivative from 1 to 6 of g of x, or the integral from 1 to 6 of g of x. So let's take a look over here. I now want the area under the curve from 1 to 6. Well, this is a little bit trickier because I can find the area under the curve geometrically from 1 to 3 pretty easily, but from 3 to 6 I have this smoother like curve. I can't just do like a triangle or find the area of a rectangle. I can only use that to approximate. But fortunately for us, they've defined what the curve is from 3 until 6. So what I'm going to do is start by taking this and breaking it up into 2 parts. I can find the area under the curve from 1 to 3 of g of x geometrically, and the area under the curve from 3 until x using the function 2x minus 4 squared dx. So remember, this just means take the antiderivative of this with respect to x. And this is going to work because this is going to give me the area from 1 to 3, and then this picks back up at 3 until the end, which is 6. So let's see if we can find the area under the curve from 1 to 3. Well, if you look up at your graph, I know you can't see it on mine anymore, but if you look up on your graph, you see you have a rectangle from 1 to 3. It's a width of 2 and a height of 2. So the area under the curve from 1 to 3 is 4. Well, now I'm going to take the antiderivative of this. You can do this a couple of different ways. Option number one is you can FOIL this out. So you would have like this, and then you would multiply it out. That's going to give you 2 times x squared minus 8x plus 16, which is really 2x squared minus 16x plus 32. So option one is you can FOIL this out, and then you can take the antiderivative using the inverse power rule. Option number two is you can do a u sub where x minus 2 is your u. Now we do have a shortcut, and the reason we have a shortcut for this one is because x minus 4 is linear. The derivative of this is going to be 1, which is a numerical value. So my other option is for this piece, this would be replaced with u, would be my stuff. So if I'd u squared, the antiderivative would end up being u to the third. I'm going to divide, oopsies, I don't actually want to put that there. It would be stuff to the third, then I would divide by 3. So I'm going to divide by 3. My stuff isn't going to be u, in this case it's x minus 4 to the third, and then I can divide by the derivative of stuff. Well, the derivative of this is 1, so I don't have to write it. So I can actually use the shortcut this time. I'm just doing it like the antiderivative stuff, and then I'm dividing by the derivative stuff, which was 1. Well, we still need to evaluate this from 3 to 6, and I want to be really clear that I'm not evaluating this all the way through the 4. The 4 is separate. I'm just evaluating from 3 to 6 for this piece here. So I have my 4 on the front, plus I'm going to plug in 6 first, minus, now I plug in the 3, and again I can just stop here because this is a numerical answer. Okay, so again I did it with the shortcut, but if you want to go out and do it with the u sub, or you can use the inverse power rule with this, you can do that as well. So now let's look at part C. It says from -5 to 6 on what open intervals, so that's a nice, we just know that we only have to use parentheses, we don't have to worry about brackets. So on what intervals, if any, is the graph both increasing and concave up? So the graph of f, increasing and concave up. Give a reason for your answer. Well, if we're talking about f, and I want to know where f is increasing, I really just want to know where the derivative of f is positive. Now the problem here is I don't have a graph of f. Well, we do, we kind of talked about it a little bit, but they gave us a graph of g, but we know that g is f prime. So I'm actually going to use in my justification g, but we just need to make this connection somewhere. We actually wrote at the top of our paper already that g and f prime were the same. So even though I'm looking for where f prime is greater than 0, graphically I'm going to look on the graph of g, so I'm going to use that in my explanation. Okay. Now let's look at concave up. Well, f is concave up when the second derivative is positive. But since we're looking at the graph of g, we need to think about what's happening for g. Well, we already know that g is equal to f prime. So if I want to know something about the second derivative of f, that's going to be the first derivative of g. So again, if I want to know when the second derivative is positive of f, it's the same as asking when the first derivative of g is positive. Well, that means I'm looking for where the slopes are positive. So another way of thinking about it is I'm really looking for where g is increasing. So again, I'm looking for where g is positive and where the slopes are positive, where it's increasing. So if I look up here, g is positive essentially everywhere from 0 until 6. At 4, it's 0, but we're not going to worry about that quite yet. So it's positive everyone from 0 to 6. The slope is positive from 0 to 1 and also from 4 to 6. So the places where it's both positive and increasing is 0 to 1 and 4 to 6. So I can say f is both increasing and concave up on 0 to 1 because I've made clear statements about f and g, I can really use either at this point, but I'm going to use g because that's what my graph has, because g of x is greater than 0, and we can either write g prime of x is greater than 0, or you could write g is increasing instead of this. Okay. If this were on the AP exam, you'd likely get 1 point for this interval here, and then 1 point for your justification. So now let's look at part D. Part D says find the x-coordinate of each point of inflection on the graph of f. Well, points of inflection happen when the second derivative changes sign. So each other changes from negative to positive or positive to negative. Well, remember, the second derivative for f is the first derivative for g. So really I'm looking for where does the first derivative change sign of g? Well, if I'm thinking about g prime, I'm thinking about its slope. So when are the slopes changing from positive to negative or negative to positive? Or in other words, where is g changing from increasing to decreasing or decreasing to increasing. Now, I wouldn't use that notation when I'm writing my justification, but I'm just going to use that for right now. So let's take a look. So if f prime is at the sign, I want to know when the first derivative of g changes sign. So when is it changing from a slope of positive to a slope that's negative? Or where am I changing from increasing to decreasing? Okay, well, this isn't increasing or decreasing. I'm increasing, but I don't change to decreasing. I'm increasing, but I don't change to decreasing. I'm neither, and then I start decreasing. This is the first place where I actually change from decreasing to increasing or increasing to decreasing. Really, I'm just looking for my mins and my maxes, and the only place I actually have a min or a max is at x equals 4. Okay, so down here I can say f has a point of inflection at x equals 4 because g prime of x changed from negative to positive. Or you could write because g changed from decreasing to increasing. We only had one point of inflection, so I could just talk about the specific case of negative to positive. I don't have to say or positive to negative, because in the specific case, this is what was happening. Okay, so I hope that was helpful for you guys, and I will see you for your test next week.